Okay, so this is going to be where we start in the organic molecules. We're going to be focusing on several different things in this. We're going to be focusing partially on the... Did you have your clicker?
Yeah.
Okay. So we're going to be focusing on naming at first. Go ahead. Oh. There you go. Okay. So we'll have naming first, and then we're going to have to talk about what is an organic compound, right? And one of the things we're going to have to talk about is arrangements. You may have already sort of encountered this in biology, actually, where the arrangement of a molecule determines its function when you're talking about biology, right? So this is the overall topics in your sections of your book, right? And I broke down my sections as well. So the organic compounds is going to be composed mainly of carbon, hydrogen. They can also contain oxygen, nitrogen, sulfur, phosphorus, and there are other elements. These are the major ones that we'll be concerned with. The vast majority of organic compounds will be carbon, hydrogen, oxygen, and nitrogen. Okay? But sulfur is actually quite important, especially in biological systems. Biomolecules, these are going to be things like proteins, carbohydrates, lipids, and DNA. They're all organic compounds. Essentially everything you think of as being in living organisms are going to be organic molecules. Okay? Now please note that this is a different definition than organic farming, which actually has no clear definition at all. So, do you guys know that? Okay, if you ever want to see something that's just nuts, look into organic farming and the rules by which something can be listed as organic farming. And it is wild. There is no clear guidelines. Some of the stuff they sell you guys for twice the price is just wow. Okay. So, the condensed structural formulas are going to show all the atoms in a molecule, but we're going to minimize the number of bonds to be as few as possible. The condensed structures may or may not show the lone pairs. Just depends on if we got lazy or not, right? So the molecular formula is going to show only the number of each atom in the molecule. This is the one that you are sort of most familiar with so far. It's what we've usually been using, okay? And the Lewis structure here, this is going to show all the connectivity of all the atoms and all the bonds. So you know what's connected to what and how it's connected, okay? Notice that the Lewis structure does not actually tell you the three-dimensional structure, does it? It's a flat paper structure, right? Two-dimensional. Okay. This right here is the molecular formula. See that you just grouped up all the carbons, hydrogens. You really don't know how these things are connected. They could be connected a whole bunch of different ways, right? Just like a puzzle or Legos, right? We have 3 of these type of Legos, 8 of these type of Legos. There we go. Build what you will. This is the condensed structure. This actually gives you a pretty good idea of how these things are connected. If you look here, this C is connected to these H's, right? How many bonds does a hydrogen want? 1, right? How many bonds does a carbon want? 3. Not 3. 4. Yeah. Okay. And then, so this right here has 3 bonds that are hydrogens, right? And then this one's connected to that one. This one then has 2 bonds that are hydrogen. It's connected to these 2 carbons. Can everybody see that from there? Yeah, you just go along like that. Okay? And so it actually gives you a pretty good idea of how things are connected, just from the condensed structural formula. But if you want to make sure that you express it so you can actually see the bonds and make sure, hey, that is a double bond there, that's a single bond, etc., this is the Lewis structure. What you'll actually often find is these 2 right here get blended quite a bit. Okay? There's usually a lot of a structure that we just don't care about. And then one specific area that we're like, this is interesting, and we'll draw it as a Lewis structure. Okay? And so you're going to see that a lot. like in test questions, you'll see that if you ever look at pharmaceutical information, you'll see that all over the place. Okay, very, very, very common. All right. Now, let's talk about a few other different types of structures. So, skeletal structures. These are going to be like the skeleton of a human being drawn out, or skeleton of a bat, right? You get a very good fleshed out sense of what it looks like, but you don't have every detail, do you? Okay? So it's simplified. So these are going to be our bare bones structures. They're going to show the bonds between the carbon atoms as lines. We'll take the bonds, the hydrogen atoms, and we won't show them. Why don't we need to show them? Because hydrogens only make bonds, one bond, right? And so hydrogens just fill in all the carbon empty spots. That's all hydrogens ever do. Okay? So again, these skeletal structures, or line edge structure. By the way, this is far more commonly called line edge. I'm using your books thing because I don't want to confuse you from your book. And you go, why is this completely different? But your book actually uses something that's incredibly rarely used. Other than your book, I don't think I've ever heard anyone call this a skeletal structure. So usually it's called a line edge structure. Yeah. But anyways, as long as you know how to do it, you know what it looks like, and you can read it. That's the main thing I'm worried about. All right, so right here, this is the molecular formula. This is the condensed structure that we talked about. This is the Lewis structure right here. This one right here is what your book calls the skeletal structure. Every other book and every other person on the planet calls this a line edge structure. Okay? And why it's called typically a line edge structure is everywhere where a line ends, those are where carbons are. Okay? So right here, there's a carbon there, carbon there. The lines are always bonds. Okay? And so this is a single bond here and here. You never bother filling in the hydrogens on carbons because they just filled up to be 4, right? So if we look at this carbon on the end here, it has one bond to it already. And so how many hydrogens would it have to have? Exactly. The remaining, which is 3. You got it. This one here has 2 bonds to it. So how many do we have to fill it up with? 2. Exactly. 2 hydrogens filled up, right? And see how easy that is? Like you can just automatically do it. So you save yourself tons of time in having to write this stuff out, don't you? Especially, keep in mind that like a normal structure for a protein is thousands of carbons long. Structure for like a fatty acid is 20, 30 carbons long. Okay? So these things get long when you start writing out some of the biomolecules. All right, now, if we don't have a carbon, what do you think we do at the end of that bond? Let's say this one here was not a carbon. What would you put there to make sure everybody knew that's not a carbon? The atom, yeah, whatever it is, right? You'd put an oxygen, a Cl, nitrogen, right? In the case of oxygens, Cl's, nitrogens, Cl's you don't really have to worry about this, but you would also go ahead and express that they have a set number of hydrogens, okay? Because they tend to have some interesting stuff happen to them, and so you need a little bit more expression there. Okay, so let's go ahead and look at the rules for drawing out skeletal structures. So the bonds to carbon are going to be shown. Bonds between carbon and hydrogen not shown. They're implied by the number of bonds carbon normally would want to make. Other elements that bond to carbon are going to be drawn at the end of the bond. They'll use their symbol from the periodic table. If these atoms have hydrogens bonded to them, you will have to express the hydrogens in those cases. For example, alcohols are OH. And so you always express the O and the H together as one group. Lone pairs of electrons are typically not shown unless you really want to stress them as being there. Okay? So if it's something very important that has that lone pair shown, you'd show the lone pair. Otherwise, don't bother. You're trying to do this quick, right? People can figure out the lone pairs on a chlorine. So right here are some examples where we have the Lewis structures, and we're going to go ahead and draw out the line edge formula, or the skeletal structure, as your book says. Again, these are just the carbon skeletons so far. This is the first steps, right? And so we go ahead and draw these out. Whenever you draw these out, one of the things you have to keep in mind, you really have to pay attention to, is the number of carbons, okay? It's very, very easy when you're drawing these things out to just start drawing away and then not keep up with counting. So whenever you draw a structure out, always count out the number of carbons. Do I have the correct number of carbons? Okay? Very common mistake. Like 70% of mistakes as you're starting is going to be this. You're going to go and do something that's 4, and you're going to put one extra line. And then that would be 5, right? And now you no longer have the same structure, do you? Yeah. Okay? So draw these out. So all the bonds between the carbons. So alkanes are going to contain only single bonded carbon and hydrogen. They're what's called saturated typically, so saturated hydrocarbons. Anybody ever heard of saturated fats? Yeah, that's saturated hydrocarbons. Okay. The chains on the fats are saturated. They have all hydrogen. Hydrocarbon is going to indicate that the alkanes are made up entirely of hydrogen and carbon. Saturated indicates these compounds contain only single bonds. They don't have any double or triple bonds in them. What does an unsaturated fat mean then?
Double bond.
Yeah, usually a double bond. It could theoretically have triple bonds, but those are extremely rare. And some of them have more than one double bond. So. And by the way, if anybody's curious, the beta, omega, that sort of thing in the saturated fatty acids, the saturated fats, those actually indicate where the double bond is. Okay. So each of the carbon atoms, in addition to being bonded to other carbon atoms, is going to be bonded to the maximum number of hydrogen atoms. This is what's saturated about it. If it doesn't have the maximum number of hydrogens, then it's unsaturated. It hasn't been saturated completely with hydrogens. So these straight chain alkanes, these are going to be made up of carbon atoms. They're going to be joined to one another to form continuous on-branch chains. They'll be of varying length. We have lots and lots of different types of hydrocarbons. You may kind of already know this because you can get various different hydrocarbons and buy them. Anybody ever heard of natural gas? No? Use a lot in burners? Like a house? Bunsen burner upstairs? We use natural gas? Okay. So those are hydrocarbons that have links between 1 and 3 carbons long. Okay. If we're looking at propane, anybody ever get any propane or propane accessories? I'm sorry, I couldn't resist. That was a King of the Hill reference for all the youngins, which is a great show. Check it out sometime. So that one right there is propane. We usually use it in a grill, right? That is a 4 carbon long chain. Anybody ever look at the pump when they're pumping their fuel for the vehicle? Gasoline. It says octane rating on it, right? Octane is a specific chain length of carbon. It's 8. Okay, so the first 4 alkanes are actually historical names. They're still in use today. Each compound is going to give it a name based on its carbon atoms in the chain. And so the naming is actually literally how many carbon atoms, and then does it have single, double, triple bond. Okay. The names of the straight chain alkanes with 5 or more carbon atoms are going to be your Greek prefixes. They're going to be followed by ane. A-N-E is what's representing that only has single bonds. Okay. This is the generic formula of a ane and alkane. Notice the alkane name. Alk meaning it has some length. Ane meaning single bonds. Okay? It's me saying straight chain, carbon chain without specifying the exact length, right? Okay. So we have here, C, this is the number of carbons if we take that number of carbons, we would go H, 2 times the number of carbons, plus 2. So if this was 2, C2, ethane, then this number here would be 2 times 2, 4, right? Then plus 2. So that would be H6. So the formula for an alkane that's too long is C2H6, right? Okay. All right, so this right here is your alkanes and their naming. You're going to want to learn this language. That's part of what this course is, right? It's partially a language course, isn't it? We're learning what language? Language of science, right? So we can understand when somebody tries to bamboozle us. Okay, so meth. By the way, anybody ever heard meth before?
Yes.
Guess what that's named after? There's a specific methyl group, like single carbon CH3, that is, if it's one way on the meth compound, as in the drug, it's active. If it's the other way, it's inactive. And so that's actually what that's named after, in case you're wondering. So methane, me, there's only one of me, right? Methane, single carbon. It's going to have a CH4, because 2 times 1 plus 2 is 4, isn't it? Okay. Okay, it does not have a skeletal structure, because technically that would be a dot, wouldn't it? So you can't really write out a skeletal structure for methane. Ethane, eth. Anybody ever done a paper around here and had to write out et al? Yeah, author name et al. Yeah, so that's actually the root word here. Et meaning 2 or more, right? So et al was always, there's 2 or more. Ethane, 2. Okay? It's Latin, by the way. That's why it has that root. All right, so ethane, this is going to have 2 carbons. Actually, this would be a straight line. I don't know why your book's table here, I took from your book, doesn't have it. But, yeah. Anyways, straight line. Just prop, as in propeller or propane, right? Okay. So propane has 3 carbons. Actually, one of the easiest ways to sort of remember this is propeller 3 has usually 3, right? That's where the name actually comes from. But if that makes it confusing, you can also remember, do you know what a pro baseball player's batting average is? A really good one? 30%. So if you hit the ball 30% of the time in baseball, you are really great at your job. Which I always find amusing, right? What other job you get paid millions to be on the game 30% of the time and screw up 70% of the time? Okay. Butane, this is going to be 4. I'm going to make one that's kind of lowbrow humor here, okay? So excuse me, but it's incredibly memorable, okay? How many cheeks do you have? 4. 2 on the top, 2 on the bottom, right? Buttane, right? So, yeah, it's lowbrow humor, but it is so memorable, isn't it? Yeah, so 4 cheeks because your butt, right? Butane. Okay. Pentane. Everybody's heard of pentacle, right? Or pentagon. Yeah. So pentane, 5. Hex is in hex wrench or hexagon, of course, 6. Hept. There's not really a really good one for hept. It's just not widely used. It's heptagon, technically, 7. Oct, as in like octane, which is 8 carbons long, as in octopus, right? Which has 8 tentacles. Nonane, that is 9. There's not really a really great one for you to remember that one either. Technically, there's the Greek goddess of childbirth, which was where that root came from. 9 months for childbirth, so 9 carbons, nonane. Dec, as in decade, 10, right? Okay. So decane, decade, 10. 10 carbons. Cyclo,
If there's a structure that's over 10, does it follow the same rules as in geometry? Like it would be like, instead of like, it'd be like 11 agon, it'd be 11 ane, 12 ane.
Yes, it would follow the rules for the Greek. Just like the hexagons. Yeah. Typically, though, you kind of just give up after that point. So chemists are kind of lazy, and we sort of just do cutoffs. So usually, you're never going to have to deal with a beyond 10 carbon chain where you actually have to name it like that. At that point, you're just going to have names where it's like lauric fatty acid. Yeah. And so it'll have its own naming because it's too damn long and nobody wants to remember. Yeah. Okay. And cycloalkanes, these are going to be rings that form alkanes. So the names of the cycloalkanes are going to be just formed by putting cyclo in front of your alkane name. So for example, here we have 3 carbons in this. So that is cyclopropane, right? Cyclo because it's a ring. Everybody see that okay? This is the smallest possible ring. Can you connect back into a ring structure with only 2 points? No, that's a line, isn't it? 1 point, that's not even a line, is it? Yeah. So you have to have at least 3 carbons to make a ring. So that's the smallest ring. Most of the rings that you're going to experience in nature and you all will see and be able to actually interact with in life are going to be 5 and 6 membered rings. 3 membered rings are very, very uncommon, very rare, and so are 4 membered, etc. Okay? 5 and 6 membered rings are very, very common. Okay. So this right here is some of the different rings. This is cyclopropane, cyclobutane. This is the more common ones, cyclopentane and cyclohexane. These rings are actually very common in biology, included. Okay. Anybody ever heard of cholesterol? Or hormones? Yeah. So those are actually cyclic structures. They're actually a combination of these 2 ring structures combined together into one. Okay? So the alkanes, these are going to be non-polar compounds. Anybody ever heard of like combines with like? No? Okay, how about this? Anybody ever been at a gas pump when it's raining? Okay, what do you see for the puddles? Do they look normal? They don't look normal, do they? No. So what ends up happening is that you have water that goes into the puddles, right? Those are the puddles. And then you have this shiny surface on top, don't you? And so that's actually the hydrocarbons that we're talking about right here. Those are the alkanes that leaked off of those gas pumps. And they're floating along the top because they don't mix with the water. This is because they are what is referred to as nonpolar, meaning they don't have poles for the entire molecule. Remember that? Where we did polar bonds. And we talked about after the Lewis structures and the 3-dimensional structures that things could have poles for the entire molecule. These won't have poles for the entire molecule. Okay? So the electronegativities of carbon and hydrogen are so similar that 2 elements form covalent bonds. They don't tend to have clear poles along those bonds, and so the overall molecules are nonpolar because they don't have any clear poles. Nonpolar nature of alkanes actually affects the behavior of these compounds whenever we're in an aqueous system because water is polar. Anybody ever had the Legos with the magnets in them and the Legos without the magnets in them? When you were a kid? No? Man, everybody's deprived of the magnetic Legos these days. That example used to really work, and then all of a sudden it doesn't. It's like a wall happened. Okay, maybe they ran out of money for magnets at Lego. It's a thing. So what would happen if I threw a bunch of marbles and a bunch of magnets in the same bag and mixed them? Would the marbles and the magnets mix? No, no. All the magnets would group up into one clump, right? And all the marbles would get excluded out of that clump, wouldn't they? Okay? And that's the exact same thing that happens when you mix or try to mix polar and nonpolar substances, like oil and water, gasoline and water. Is what happens is your water all clumps up together because they're little magnets, aren't they? Okay? And then all your nonpolar compounds get squeezed out and excluded from that. And so they just end up in their own area by themselves. Because they're nonpolar, they don't stick together with the magnets, do they? The polar stuff. Okay?
Which compounds are they gonna affect in the aqueous systems?
They're not. So that's what I'm talking about. Aqueous is water, right? So water is polar, and so what's going to happen is all the polar water and all the alkane, which is what we're talking about, the nonpolar compounds, they're just going to separate. Yeah. They won't mix. Yeah. And you know this pretty well, actually, if you've ever taken like oil and water, you reheated some food, all the fats ended up getting floating on the top of your water, right? Yeah. That's actually this, right? Okay. Now, soap does help to break that and allow them to mix a little. And we can talk about that sometime, but I kind of have to get you through the set amount of material, right? Okay. Okay, so alkanes, you're probably the most familiar with them as a fuel source, and that's because they readily undergo combustion, which is the reaction of an alkane with oxygen. Produces CO2 and water. You probably knew the CO2 part, but many of you probably didn't know the water part. Has anybody ever been following a car that's running when it's really cold out? Okay. Everybody saw the stuff coming out of the back of the car? That's like a whitish color? Okay. That's water. So what you're actually seeing out of the back of the car that's white colored is the water hitting cold air and freezing into crystals. Okay? And that's actually what clouds are as well. See the clouds up there? Yeah, it's frozen water suspended up in the air. Okay? The mist is actually liquid water suspended up in the air. All right? Now, can anybody tell me, whenever you see those iconic photos of pollution, where it shows this stack and it has this white stuff spewing out the top, what are they actually taking a picture of? Yeah, steam. Yeah, technically it's frozen water, right? But yeah, they're just taking a picture of water spewing out the top of those. I always find it amusing. They always do that because it shows up real nice, right? And shows up real pretty. But why don't they do the steam stacks where it's not working correctly and it's spewing out black at the top? That's actually super problematic. That's a photo that says wow, this is damaging. Whenever I see the ones that they're like, we're killing the planet, and it's steam coming out the top of it, I'm like, what a crappy photo. That's just such a damn dumb photo. Okay. So scientists are currently searching, of course, for a cleaner, cheaper hydrocarbons fuels to replace fossil fuels. Alternatively, we're looking for a complete replacement of just non-fossil fuels, non-hydrocarbon at all. We're kind of unsure which way that's actually going to go. Does anybody know what else is used for the hydrocarbons from fossil fuels, by the way? What other uses there are? Okay, energy is a big one, but actually everything you wear and use around you is fossil fuels as well. Like your clothing right now has fossil fuels in it. Your phone, fossil fuels. Your computer, fossil fuels. Your cup, fossil fuels. Your your makeup, if you have makeup, fossil fuels. Your shampoo today also probably had some fossil fuels involved. Because it's called it's called as feedstock. It's where we get all the carbons to do the reactions and make all the stuff. So like you smell spearmint, probably fossil fuels. Okay. Now, this right here is your simplest organic compounds. This is going to be methane, propane. This is isooctane. This is actually the form of octane that is referred to as octane in your gas. Okay? Though, realistically speaking, modern day gas does not actually have this form of octane as the octane they're mentioning. Okay? Modern day gas is a very careful blend, so that burns like this. Okay? It's actually why they have to put ethanol in it, in case you're curious. Is because it actually helps it to burn more like isooctane. Anybody know what happens if you don't burn like isooctane? No, it won't catch fire. What will happen is that your engine is calibrated to work at that burning level. Okay? And anybody ever heard knocking? Your engine's running? Yeah. That's because you're no longer calibrated, or you're no longer burning fuel that is correctly calibrated to that. So you're not isooctane like. Yeah. You have too low of an octane rating usually. I know, right? Okay, so this is actually the Beyond Decade. So this is hexadecane, and it's like a Greek system, right? And so hexadecane, that's how you go about going longer. It's very rare to actually see that, though. Like, I maybe see these where they actually go beyond a 10 chain once every, I don't know, once a year or so. Yeah. Typically, these would actually be referred to by their names. For example, this right here is one of the major components of diesel fuel. So if you're ever looking at diesel, it's the heavier chain ones, the longer chain carbons. Gasoline is the shorter chain. Propane is the 3-carbon one. Butane is the 4-carbon one. And then natural gas is actually 60-ish, 70%, depending on where you are. Can get up to 90% some places. Methane, and then you'd have some ethane and propane in there as well. Okay? It's actually funny because depending on where you are in the country, your temperature for natural gas will change, how hot it burns. So they can actually be very different. Anyways, this one right here is candle wax, which is the paraffin wax, in case you're ever curious. So whenever we have elements that are not carbon and hydrogen that are present in organic compounds, these are going to be called heteroatoms, literally meaning different atom, right? We have an other atom. The group of atoms that's bonded in a particular way is going to be called a functional group. These are going to be things like double bonds, triple bonds, but also alcohols. Anybody ever heard of formaldehyde? Okay, that's named after its functional group, which is aldehyde. Okay? A lot of the names you know are actually functional groups. Many of the compounds that you've heard of or experienced were actually the name of the functional group that you know. Okay? Anybody ever heard of acetic acid? No? Okay. It's actually mentioning its functional group, and that's vinegar. Okay, so the compound, organic compounds are going to be classified into families based on these common functional groups. These are called functional groups because they're where you have interesting chemistry happen. Okay, so aldehydes all tend to act a little bit similar and do similar things chemically. Acids, carboxylic acids, all tend to do the same things. Alcohols all do the same things. Anybody know that? Whoopsie. Anybody know that you can actually get drunk on any alcohol? You know what happens if you take the other alcohols, though? Okay, anybody ever heard of people going blind because of moonshine? That's if you have too much methanol, which is wood alcohol, in your moonshine. Okay? Methanol being the single carbon one. Ethanol being the one normally people would be drinking. Okay? If you can drink like propanol, or you drink you know, the windshield cleaner fluid. Those are long chain alcohols. People do that because they can get drunk. Then they get horribly sick and die. Yeah. So please don't do that. That's not an invitation. Okay. All right. So some of your functional groups, alkanes, alkenes, alkynes, and aromatics. These are actually just hydrocarbons. They're then going to be families of organic compounds. They'll just contain carbon and hydrogen. They're just different arrangements of them. This is single bonds. This one's double bond. This one's triple bond. Okay? And so see alk meaning I don't want to specify the number yet, do I? Okay? Ane means single bond. Ene, double bond. Ine, triple bond. If you don't want to sound stupid later on when you're trying to do this, go ahead and try it with me. Ene, double bond. Ine, triple bond. Okay? Now I will warn you that the southern accents tend to have a bit harder time with this differentiation. It's one of the things you got to watch for if you're a southern accent. Okay? Okay, so most functional groups are going to contain, most common heteroatoms are going to be the oxygen, nitrogen, and sulfur. Many functional groups are going to contain a carbon double bonded with an oxygen. It's an extremely common functional group, and it's a lot of the different functional groups. So this right here is actually what's called a carbonyl. It's a carbon double bonded to an oxygen. There are actually a bunch of different functional groups that all have this in them. Okay? Aldehyde has a carbonyl in it, as in the formaldehyde. Okay. All right, so the functional group is going to be the reactive part of your organic molecule. That's why it's called functional, right? Because it has function to it. To keep the focus on the functional group, we're oftentimes going to put R. This actually represents the rest of the molecule. The actual, what the term is for is residue, as in the rest of the stuff that would come off. Okay. The use of R, again, allows us to simplify it, so we're just looking at the functional group and where we're actually interested. The R saying, hey, I don't care what all that rest of the stuff is. Okay. R can actually represent anything. It could be one carbon, it could be 20 carbons, it could be a whole series of functional groups off there. We just don't care. Okay? We just care about the one functional group, one area that we're trying to look at. Right? It's like when you blur your eyes and focus in on something, right? What's the rest of the picture? I don't know and I don't care. Okay. By the way, problem with modern cinematography. They keep everything in focus, right? You don't want that. You want to just pick up the one thing you want to express, right? Yeah. A lot of science is going to be simplifying and getting rid of excess information so you can focus in on something you actually want to learn and want to understand. So right here we can actually see some different R groups and groups that we could make R's. We can also see the different functional groups. So right here, this is actually fatty acids off of glycerin. And this is actually how most fatty acids would be in your body. Okay? So that's how most fats are actually in your body right now. This right here is an aromatic compound. These are derivatives of what's called benzene. That's benzene right there. It has that alternating double bond structure. Okay? And that's what's referred to as aromatic. By the way, that's an important part of niacin, which is the vitamin B3. So right here we actually see different alcohols. The alcohol is a OH group connected to a carbon. And whenever we look at these alcohols, we can see that they usually end up being called primary, secondary, and tertiary. And what that's telling you is how many carbons the carbon units involved in the alcohol is attached to. This one has one other carbon attached. That's that R group right there. This one has two R groups. This one has 3 R groups around it. Okay, this right here is what's called a phenol. It's actually an alcohol with an aromatic ring. So see the little alcohol on that aromatic ring? Okay. And these are just the different biological compounds here. My God, this thing is so low resolution, isn't it? Yeah. So I would recommend, actually, you might want to print these off. They're high resolution images on mine. Okay? And so you can actually print these off, and then you'll have little tables. Okay. This right here is an ether. Everybody ever heard of an ether? As in like ether that can be used to put somebody asleep? No? Okay. Not at all? Oh, that's just sad. So this is actually what used to be used as an anesthetic back in like the 20s and 30s. And actually comes back every few decades because it's very cheap. And as long as people are responsible with it, it's actually very effective. Okay? It's also incredibly cheap to make. And so, for example, you know how we have the fentanyl problem now? Back in the 1800s, they had the ether problem. And they used to be called ether eaters. It'd literally be people that'd take little droppers and put the ether. Apparently, you get like the whole rotation of being drunk, everything, within like over a 10-minute period. Yeah. So people used to do it on like their lunch breaks, essentially. Yeah, pretty crazy stuff, actually. Okay, so this right here is a thiol. You'll notice it's like alcohol, right? Except it has a sulfur instead. Okay, so it's an SH attached to something. This right here is a phosphate. Anybody ever heard of DNA? Yeah? RNA? Maybe ATP? Okay. The P in ATP stands for phosphate, right? Triphosphate, in fact. This right here is ATP. The phosphate backbone for DNA, that is phosphate groups linking between sugars, which is this stuff right here. Okay, so this is the amines right here. So this is primary. It only has 1 carbon attached. Secondary, 2 carbons attached to the nitrogen. Tertiary, 3 carbons attached. Anybody ever eaten fish? Smells fishy, right? What do you do to make it smell and taste less fishy? They always serve it with what? Lemon. Yeah. So if you put acid with it, what you can do is you can take the amines, which is why it smells and tastes fishy. You put acid with it, it'll protonate the amines and make right here the quaternary amine, which is the ammonium salt. Those have very high melting and boiling points, and so you don't smell them very much because they don't go up into the atmosphere as gas. Yeah. And so, ta-da, smells and tastes less fishy, right? Yeah, you get more of a potent taste too because it dissolves easier. Okay. Also, what you do to things like crack, in case you're wondering. If you ever look at the back of a label for a drug and it says .HCl, that's what they're doing. They're protonating it. Okay, this right here is an acetyl group. This is very common in things like fatty acids, and right here is this is the you probably don't know that one. Actually, now I think about it. Aldehyde, this is like formaldehyde. Anybody know why the mortuary person always has that stereotype? Like really pale, red eyes, tired, lethargic, very little emotion expressed. You all know that stereotype, right? It's always in every horror movie, every time you see a mortuary, in any movie, it's always that, right? Okay, that's actually formaldehyde poisoning. And so lethargy, less emotional expression, you start getting weakened, and so you get pale, and you also have red puffy eyes because it's affecting your sinuses. Yeah, that's formaldehyde poisoning. They're working in substandard conditions. If you ever see a mortuary person that looks like that, you get them outside and get some air. Okay? They're breathing in too much formaldehyde. Right? Okay, this is a ketone right here. Anybody heard of like a ketogenic diet? Ketones? Yeah. Ketone bodies specifically. Carboxylic acid. This right here is, okay, who's here is from Tennessee? Is a true born Tennessee. Do you like vinegar? Everything in this state has vinegar in it, right? Like stuff that, why in the hell does it have vinegar? I don't know. But it has vinegar. So this right here is the acid that is vinegar, okay? It's carboxylic acid, specifically acetic acid. It has 2 carbons. In case you're wondering, anybody ever seen Asian beetles? Anybody had one bite you? Or ants, the small ones. Ever had that bite you?
Formic acid.
Huh?
Formic acid.
Exactly. Yeah, that's the 1 carbon. Yeah. And that's that smell when you crush the Asian beetles or you crush a bunch of ants and you smell like that fresh cut grass. That's formic acid. Okay? The reason it hurts when they quote unquote bite you is because they're spraying you with formic acid. It actually tans you. Like, as in tanned leather to your flesh. Yeah. So it harms you. This right here is carboxylate. This is the basic form of this. It's lost the hydrogen. Okay? And that's what happens to vinegar when you put a base with it, in case you're wondering. This right here is an ester. These typically are known for their smells, actually. A lot of the compounds that you smell and go, oh, that smells really fruity and nice, those are usually esters. Okay? Very common in esters. This is an amide. This is the linkage you would see in a protein. Anybody ever heard of like a peptide bond or anything like that? Yeah, that's the peptide bond. That's an amide. All right. So the unsaturated hydrocarbons, let's talk about the alkenes. This is one with a double bond in it, right? This could have more than one double bond, but the ene part means it has a double bond. It's unsaturated. Again, these are going to be unsaturated because they have more than one bond between 2 carbon atoms, and so you have less hydrogens than you could possibly have, right? You are not saturated with hydrogens. The double bond is going to be shorter and stronger than a single bond typically. Alkenes are going to react in what's called addition reactions. It's where you add stuff across the double bond and break the double bond. Okay? Anybody ever heard of peanut butter? Okay. Anybody know what peanut butter is? It's peanut oil that has underwent hydrogenation, which is an addition reaction. So peanut oil has a double bond on it, and that's why it actually doesn't congeal at room temperature. It's liquid at room temperature. Okay? Used to be used in fryers a lot, actually. Funny enough, the thing that they keep protesting oils that are used in fryers at things like McDonald's. Every time they've done that over the last 60 years, we go to a more unhealthy oil. So we're just have continuously moved to less and less healthy because of protests, because the thing before was unhealthy. Anyways, so peanut butter is where you take that, you're going to break the double bond, add a hydrogens across it, make it a saturated alkane, and then this is actually going to cause it to have a higher melting point. And so peanut butter, solid at room temperature, right? You put it on toast or you put it on something hot, what happens to it? It becomes liquidy, right? Yeah. So that's what peanut butter is. The alkenes are more reactive than the alkanes, typically. This right here is an alkene. It has the double bond right there. This is specifically ethene. And these contain at least one carbon-carbon double bond. They can have a multiple of 5 carbons, by the way. There can be many options. Some of the common terpenes are going to be beta-carotene and D-limonene and alpha-penene, as in like the beta-carotene you get from spinach, right, or carrots. Okay, and these again are the terpenes. They are going to have a double bond and a multiple of 5 carbons. Cholesterol, testosterone, and estrogen are actually synthesized from terpenes. You would actually take the terpene, which is a long chain with double bonds, and you break it and form these ring structures. And that gives you the cholesterol, testosterone, and estrogen. So let's go ahead and talk about alkynes. Alkynes are going to have a triple bond. Okay? And so again, they're going to be unsaturated. Your triple bond is going to be shorter and stronger than the double bond. The alkynes are going to be even more reactive usually than the alkenes. There's actually more reactions you can do. Also, almost all the reactions that you can do with an alkene, you can also do with an alkyne. Okay? So, alkynes are pretty rare in nature, actually. You don't see them a lot because they're a bit more reactive, especially under these sort of biological conditions like they would be under. And so, they don't tend to exist for a lot of time. But, for example, right here is an example of an alkyne. And so, this is actually a toxin, in case you're curious, and it has two alkynes actually right there and there. Okay? It's actually a toxin that's secreted by this frog right here to make it so you don't want to eat it. Okay? All right. And so this right here is aromatics. These are actually very common in nature. They're incredibly stable. Okay? And so this family of compounds actually got its name. This is so funny. I forgot your book had this. Okay, so this stuff is oftentimes stuff that I go ahead and have from your book, and your book will say this in it, okay? Now, this is kind of amusing because aromatics actually don't have any real smell other than hydrocarbon, okay? The aromatic groups themselves have no real smell. This is something your book's actually just completely wrong about. But aromatics did get their name from one of the first aromatics discovered, which does have a very pleasant smell. But it was because of a different functional group on it. Okay? And so the history of aromatics is kind of amusing because they're called aromatic, right? As in aroma, literally named for a pleasant smell, and yet aromatics themselves, no smell. It has nothing to do with smell at all. Yeah, which is just, they probably should have just changed the name, right? Yeah, it's a kind of amusing example of history. Anyways, there's aromatic compounds that have things like ethers and esters on them, and those actually are very stable structures, and most of the really pleasant smells you think of are those, actually. So they're aromatics with another functional group that smells nice. Aromatic compounds have a cyclic structure. This is benzene right here. If you have this on something, where this is attached to something right here, then this would be called phenol. Okay? By the way, has anybody ever seen phenol or phenol? This right here? On a medicine name? Anybody ever look at the bottles that are medicines? Okay. Very, very common group to see, actually. Yeah. If you look on the bottles of your medicines, go through your parents and everybody you know's cabinets, I promise you're going to find one. Also, if you ever look for logos for pharmaceutical companies, this ring shows up everywhere. Usually like a half of the ring, where they don't show the whole thing. And that's because that benzene ring is very, very common in biologically active compounds. Okay? All right, so aromatics, again, they're incredibly stable. They're very unusually stable for what they are. The electrons in the double bonds are going to be shared evenly across all 6 carbons. This is what's called a resonance hybrid. So in this case, this is where we sort of have an issue with how we draw things. Okay? So we draw things with double bonds and single bonds, right? We don't really have a 1.5 bond, do we? Okay? But in this case, what you would actually see is all these carbons have the same sort of bond between them. So these are actually closer to like a 1.5 bond between all these things. So if you ever draw this out with Lewis structures, you actually have to draw out 2 structures. It has a double-side arrow, see that? this arrow doesn't mean reaction. It means these two structures together give you the actual structure. Okay?
But they're spinning all the time.
Yeah, and they're not actually, so it's not just spinning, it's, you can represent it sort of with spinning. But what's actually happening is these bonds are actually just fully connected. So there's actually just a giant double bond over the whole thing. And because it's covering so many carbons, it gets thinned out. Is that making some sense? Yeah, we could go more depth in it, but this is a very intro class to, yeah. Join me in more chemistry if you want. Oh, I will take you so in depth you'll never get out. You'll be trapped within it. Okay. So again, this is some more aromatics. The aromatic compounds containing 2 or more benzene rings, these are going to be called polycyclic aromatic compounds. Keep in mind that chemists are pretty lazy on their naming, okay? So we typically just give up really early in counting things. And when we give up on counting things, we just put poly, right? So I don't want to count it, poly. Okay? Just means many, right? More than one, at least. So these are going to be polycyclic, poly, ringed, aromatic compounds. So they're aromatic with that structure of continuous bonding. Okay? Okay, so some of these abbreviate PAH, by the way. Phenanthrene and benzoapyrene. These are actually 2 of these. These are found in tobacco smoke, in case you're curious. Some of these have been found to be cancer-causing or carcinogenic, though keep in mind that that is not the, slam that you may think it is. Okay? Does anybody know what has also been found to be carcinogenic and is all around you right now? Wood. Wood has been found to be carcinogenic. And so by California law, you actually have to label all the trees as possible carcinogens. And in some places, they actually do. Which is so funny. All right. So aromatic compounds also contain many plastics, but they also contain biological structures that you make in your body. They're just an incredibly stable ring that has a lot of a really amazing chemistry, but I'm not going to go into all of that. Okay? It would just be too much. This right here are some different pharmaceuticals. You'll see some of these actually have aromatic rings in them. Can everybody see those on the top? Yeah. So if we take and we open packages of medicine, we're going to find a lot of these different functional groups that I've been mentioning. There's your alcohol, there's your amine, there's another alcohol. That right there is an ether. That right there is your benzene ring, which is an aromatic, right? And so that is morphine, oxycodone, tramadol, naloxone. Very common medicines that you'd see in any hospital in the world. Okay? This is what they ultimately are composed of. So lipids are going to be hydrocarbons, specifically fatty acids. So fatty acids are going to be belonging to a biomolecules that we refer to as lipids. Okay? Fats with 1 double bond are going to be called monounsaturated fatty acids. Those with 2 or more double bonds are called polyunsaturated fatty acids. Notice we gave up counting this time at 2. Technically, you could do diunsaturated fatty acids, but I don't think anybody ever does. Okay, so saturated fatty acids are going to be long, straight-chain, alkane-like compounds. They do not contain double bonds and have carboxylic acid groups at one end. The biologically most important fatty acids are actually compounds containing from 12 to 22 carbon atoms. The ones that are shorter than that typically don't show up in most biological processes, or at least if they do show up, they're an intermediate. They get used up and make something else. Okay? Most naturally occurring fatty acids are going to have even numbers of carbon atoms. This is actually due to the process by which we make fatty acids. it's actually very difficult for our bodies to deal with uneven numbers of carbons. This right here is some different fatty acids, and these are the sources. That's probably what you've heard them as, like canola oil, right? Everybody's heard of canola oil? Yeah. Really common around here. I didn't even realize it until I start sneezing that crazy. You've all seen the canola fields, right? They're the white and yellow flowers that you see growing in farm fields. Yeah. That's canola for canola oil. This is peanut oil right here. So that's what you get for peanut butter. Right there. That's animal fats that you would typically get for like a lard or something. Palm oil, nutmeg oil, and that's coconut oil right there. The length of them usually determines at what temperature they melt, by the way. So for example, these shorter ones are typically melt if like you put it on your hand, right? These require a bit more energy to melt. Okay, this is actually the name of the specific fatty acid. So if you ever needed the name of it, that's the ones for those. Now, fatty acids in our diets, fats are going to be important, and whenever you have a balanced diet, of course, they play important roles as insulators, protective covering for internal organs, and nerve fibers. They're what all our cells are made out of. The cell membranes are made out of fatty acids. Okay? They're not just used to provide energy. So the Food and Drug Administration, FDA, actually recommends that a maximum of 30% of your calories in a normal diet come from fatty acid containing compounds. It also recommends that the majority of our fat intake comes from foods containing mono and polyunsaturated fatty acids. I'm going to be honest, I don't really respect the FDA that much. At least not for nutritional guidelines. Okay? Does anybody know what 2 years ago they said was more healthy? Let's do a quiz. Lucky Charms or eggs? Yep, Lucky Charms, health score of 70. Eggs, health score of 30. So, yeah. You know the food pyramid? Do you know how many carbs you need in your diet? You need 0% of your diet as carbs. You know what was on the bottom of the food pyramid? Carbs. So, the FDA has a terrible record of nutritional advice. It's why we have so many chronic health problems in the U.S., right? Because people listen to them. The food wheel is actually a huge step forward, though. That's much better done than the food pyramid ever was. That was just a disaster. The food pyramid, if you ever look up the history of that, you'll be shocked. Like 14 of the best nutritionists of the day had their careers destroyed because they said, if you implement this food pyramid, you're going to kill millions. Yeah, which they did, of course. So, anyways, these right here are some of the different families of organic compounds and their different functional groups. So right here we see coconut oil. If we look at coconut oil, it's mostly saturated fatty acids. It's a bit of monosaturated fatty acid and polyunsaturated fatty acid. If you look at most nutritional guidelines, they actually tell you coconut oil is quite good for you. It's not really. It kind of depends on what you're not getting enough in your diet. You need all three fatty acids, but you don't need them at the same amounts. Okay? Butter right here. There's lard. Anybody have any other questions? This is canola oil right here and corn oil. These are what are known as the vegetable or seed oils. You may have heard a lot of stuff about seed oils because Kennedy. Yeah, he really has a thing for these. Oh my God, he does. Which he's not wrong, but it's kind of an oversimplification. Yeah. So this is right here is the nomenclature for simple alkanes. The alkanes that do not have carbon atoms connected in a single continuous chain, these are called branched chain alkanes, meaning they have branches off the main base or the parent. Okay? The nomenclature, the naming rules, were established by the International Union of Pure and Applied Chemistry. This is IUPAC. They provide unique naming for any organic compound and ensure that every compound has one correct systematic name. Now, actually, in theory, it works like that. In practice, there are some exceptions that have caused problems, and IUPAC have had need to go back and patch the rules. Okay? My advisor predated them. He used to say, people would go, you have to use IUPAC naming, and he would go, I came before those bastards. He did not like IUPAC. And that's because they do some very strange stuff sometimes, where they change up naming rules, and then it just causes havoc and issues. Also, they've gotten into fights that have lasted for like 5 years, where they don't just do anything at all. So, another really contentious group that does a lot of like bickering. All right, so the names of some organic compounds have 3 basic parts. You have substituents, which are going to come first. These are prefixes. You have the parent name, which is going to be like your root. Okay? It's where everything else stems. Right? And then you have the suffixes. They're endings that you change. Remember how I was talking about alkane, alkene, alkyne? Those were actually suffixes. Okay? Ein, een, ein. This right here, again, is going to be substituents. They're your attachments that you put on here. These are those different functional groups I was mentioning. You may remember phenol. Okay? This right here was the number of carbons, then the continuous longest chain. Keep in mind those words. Number of carbons, right? Longest continuous chain. Okay? And then we have the family name, which is the suffix. These are going to be important compounds we want to group in and define the molecule by. So the naming of branched alkanes, step 1, we're going to find the longest continuous chain of carbon atoms. This is going to be what's called the parent chain or the root chain. Okay? You're going to then name the parent chain. You'll count from each end to every other end of that compound to try to find that longest continuous chain of carbons. Okay? Make sure it's continuous. It can't be broken where you like just leap over to another carbon. Okay? Gotta be very careful about that. 2, identify the groups bonded to the main chain but not included in the main chain. These are going to be known as your substituents. They're going to be things that you've substituted in place of that saturated hydrogens, right? So they're going to replace those hydrogens that were on the main chain, the parent chain. These are known as, of course, substituents. Some of the more common ones are things like alkyl groups. Notice we've changed this last part again. Those are carbon chains that are branches off the parent. Okay? And the name of each alkyl group is going to be derived from your alkane. You're going to change the ane to "-ile". So let's say we had propane, but it's a substituent instead. That's propyl, right? Okay. Anybody ever heard of isopropyl alcohol? Guess where that naming comes from? Right here, right? Notice that the one carbon is called a methyl. This is an incredibly common group, and it's where the name for meth comes from its methyl substituent. Okay? Okay, we'll start here next time since I'm actually out of time, and then we'll practice a little, okay? You all have a wonderful day. This is the sort of language that you can know what compounds are around you. You can finally crack the secrets that are being communicated.
Late, so I wasn't able to do the
Okay.